Thanks, Sarah. Yeah, thanks for the invitation. Looking forward to giving this talk. All right, so yeah, let's just get right into it. So the situation we're going to have is we're going to have a subset of the d-dimensional integers. It'll be a finite set. I'm just going to give you a technical hypothesis. It doesn't really matter. You can assume this without any issue. So just assume that the integer span of the different set is all of the integers. So in other words, say your set was one dimensional, assume that the set doesn't have a common GCD, for instance. Okay, and we're just gonna define basically the fundamental thing we're gonna study in this talk. So the n-fold sumset. So yeah, just the classical definition. Okay, so what's the purpose? So the goal is to either actually we're gonna be even more demanded. So provide a formula for at least for large n. Okay, so this is something that's been studied in the past, and I'll talk a bit more about what's been done, but this is the goal. So to just compute the cardinality of the n-fold sumset of A. Yeah, it's quite a natural question to ask. Let's just see some quick examples to ease ourselves into this kind of thing. So I'll just give a couple easy ones. So suppose you have the d-dimensional cube, then so in this case we have this. Okay, so then we can compute given this exact representation, we can just compute the formula explicitly. Okay, so that's an easy example. Let's not dwell on it too much. So then we can take the simplex. Just taking some easy things that we can easily compute because of the nature of these sets. I'll speak more about what's going on here a little bit later. Okay, maybe let's be precise about what's going on here. Okay. So in this case, the cardinality is easily computed by, I guess, by stars and bars, for instance. So this will give you this. Okay. So I guess the important thing, or what's Khovanskie type theorems are about, is both of these are polynomials of degree d in n. So that's kind of the common, or at least one common thing between these two examples. But let's look at a couple more. Okay, so the d equals 1 case, which would be the first place you might look. So suppose A is 0, A2, a set of size n. I'm not going to go over why this is true, but it turns out that maybe you might guess what's going on. It's okay, so when I say for all n large enough, I just mean there exists some n naught such that for all n larger than n naught, this is true. And so okay, so I should assume, make sure, I kind of mentioned this right at the beginning, but assume that the GCD is 1. You don't really need this for what I said, but what we're going to talk about in a little bit, this will be, well, okay. You do really need this if you want to compute this coefficient exactly. So anyways, yeah, so the point is that the n-fold sumset actually just looks like, and then so kind of what's going on is, at least for large n, we start taking the n-fold sumset. At first, like if you take small n, there might be many gaps in the set between 0 and the largest element, between 0 and this maximum here. But as we start taking more and more sumsets, these gaps start to get filled, and only elements that are not going to be in the n-fold subset for large n are going to be things that are near the boundary. That's the point. Everything in the middle kind of eventually gets filled out. Yeah. Good. So that's one example. I mean, yeah, it's quite clear that the n-fold sumset here is at least a subset of this guy. But yeah, so and my claim is that this is actually almost an equality up to a finite set. Okay, so let's look at another example. I'll just give just one that I happen to know, and so I guess the next thing is to look at two-dimensional set. So here's one example of such a thing. So of course, my set looks like this. And it turns out that an A, at least for large enough A, is going to be equal to 3n squared minus 6n plus 11. Okay. The only thing I'll say about this is this 3 is the volume the convex hull of A. Right, so the convex hull of A is a triangle of base 2 and height 3. So this is okay. This is what happens in general as well. So just worth noting. Okay, so I gave you a few examples. So here we had a quadratic polynomial, 2 dimensions, and 1 dimensions. We had a linear polynomial. I guess I should mention in 1 dimensions, this is related to the so-called, okay, maybe I won't mention. Example 2, we had the cardinality of the n-fold sumset is a polynomial of degree d in capital N, and similarly for the d-dimensional cube, we had a polynomial. So there's a nice theorem course, you probably can already guess what I'm going to say, at least if you're. So this was Khovanskie in 92. At least this is as far as I know who it's due to. Oops. Okay, I want to also demand the existence of these rational numbers. Okay, so this theorem gives us the cardinality of the n-fold subset is a polynomial of degree d for a d-dimensional set. Okay, we're not going to really dwell on this too much, but moreover is equal volume of the convex hull of A. Maybe that's not so surprising. Basically, that is saying that the sumset is more or less up to some error term, more or less the integer points in the n-fold sumset of the convex hull of your set. Okay, so it's an interesting theorem, certainly. There's still, I should mention that I think more or less we just don't understand what these are, the coefficients. Okay, we understand what CD is, but we don't understand the others. So okay. So this maybe if you haven't seen this before, this is a somewhat surprising kind of structure. I should mention there's some connections to other areas of math. I'll just mention a couple. So once for one, it's connected, at least in some sense, to algebraic geometry. Okay, maybe not the deepest theorems in algebraic geometry, but certainly related to Hilbert's basis theorem. So if, just to give you an idea of what I'm talking about, then you might look at the ideal generated by these guys, and we're going to say x to the v is, so this is a definition. And it turns out that if you wanted to study these things, okay, some sumsets naturally come out. So in fact, okay. So there is some connection here, and in fact, this is what Hovansky. This was somewhat related to the some of the work he did. There's also some relation to Ehrhart polynomials. So from discrete geometry. And if you're interested in more of this, I'll recommend you a paper that explains a bit more what's going on. But it definitely, if you've heard of Ehrhart polynomials, you definitely might, you know, you might feel that there's a similarity, at least. And so here, I'm just going to briefly mention this. I'm not going to even state it formally. So here, so K is a, say, a convex set. So it gives Ehrhart polynomials is a theory that helps you count the number of lattice points inside a dilation of a convex body. And in this case as well, you get some sort of polynomial behavior. So I'm not going to talk too much more about this because it would be, we could talk for an entire class basically on this. But yeah, I should mention this. Okay, so good. A nice. So this is the starting point of what we were thinking. So going back to Hovansky's theorem, it turns out that the methods, there's been more than one proof of this, and I'll talk about a bit more about at least one more. So yeah, I guess as far as up until this point, there hasn't been effective bounds for n sub a, at least not for a general A. There has been for some A, which I'll also talk about. So yeah, one could keep track of all the things I'm going to talk about and see if I actually do, but I plan to. So yeah, the first thing I'm going to talk about is what does this n sub a look like? This is Andrew and Alid. Okay, I wrote it precisely, but I don't think it's so. It's I don't know if it's I have in my notes that this is n squared, but I think we had proved it. So, but anyways, I should mention what W of A is.
George, just to let you know, we're missing the sort of the last right-hand most portion of your screen on a few occasions. It's like the x in convex and the exponent on W of A.
Is it better now? Oh, I see.
Yeah, that's great. Yeah.
Was there anything that was fatally missing? Yeah. Thanks for pointing that out. I see, but now with this here, yeah, okay. So this W stands for width. Just kind of a measure of how the diameter of A, say. So this gives a effective bound for n sub a. I'm going to talk about a bit. All right, I'll talk more about what's going on. So this is one of the things we proved. I'll talk a bit more about this. So it's a sort of effective bound for this n sub a. Okay, I'll also remark that I won't talk much more about this. So actually, this remark was actually the original motivation of what we were doing. So there's a couple reasons why I don't want to talk about this super formally, but I do want to at least mention that. So, so if you're not satisfied that we only compute the, okay, sorry, I should leave this here. So, yeah, so the Hovansky theorem gives you a formula for the cardinality of the size of the n-fold sumset. If you're not satisfied though with that and you want more structural information, then we also talk about this and give some effective bounds here. So I should, yeah. So and it turns out that this is actually much harder to deal with, which is perhaps the reason why I'm not going to talk about it too much. Yeah, but something that we also did. Okay, but since I'm going to focus on Hovansky's theorem, let's now talk about some other work. So
there's a question in the chat.
yeah.
So is the implied constant absolute or dependent on D?
Absolute. Yeah, this is like some 2 or something, the big O. Yeah. Actually, I have in my notes what it is. Yeah, yeah. 2 should be enough. Maybe even 1. Good. So I definitely should mention this work. So there's a recent paper of so the first author is a new student at Oxford. So it's a theorem. Okay, I see. I didn't want to say it. They provide more precise bound. In a couple of cases, I'll just mention one. So for M sub A, when the convex hull of A is a simplex. So definitely a nice result, and yeah, can recommend their paper if you're interested in this sort of thing. Okay. So good. So talked about this. Now we'll talk about some ideas. And of course, not of course, but should mention, well, I'm not going to just mention, we're going to go into depth a little bit. So this theorem was reproved later. With a different proof by Nathanson and Ruja. Yeah, so they provided a different proof of this. So they have a paper on it. It's a short paper. It's a nice read, for certainly. And yeah, so the original proof was I don't know how to put it. So it used maybe more. It used like We'll just say Nathanson and Rouge's proof was more combinatorial. I'll just leave it at that. Yeah. So they have this paper. It's also mentioned in Rouge. I mean, Rouge. Probably everyone knows that Rouge has these notes on additive combinatorics, and it's in there. It's in one of the chapters. And he implicitly kind of mentions this question of finding effective bounds for this theorem in those notes. Okay, so let me just talk about what they did a little bit. So kind of the underlying map that they define is this map phi. So remember, n is the size of the set. D is the dimension the set lives in. Right. So really, we started with a d-dimensional problem, and now we have, with the introduction, by introducing this map, we've turned it into an n-dimensional problem. Okay, that seems at least as hard, but it turns out to be a useful thing to do. It'll be useful to so we're going to do this. So we're going to equip it with the partial order. A is less than B if AI is less than BI for all I. Okay, so yeah, we have this map, and this is how somehow what we're going to use to count number of points on the n-fold sumset. And how do we do that? Well, of course, NA is just equal to the right, so yeah. Okay, so we're increasing the dimension, so this is not going to be like so this map's not going to be injective, so it's an obvious issue. Right, so we're gonna what's the easiest picture to have in mind? Probably the easiest way to have a picture is to think of the one-dimensional case. And so you're going to be matching, if your set has size n, which could be large, you're mapped into a one-dimensional space, so you should expect a lot of collisions. And of course there are. But they find a clever workaround. So the idea is to forget about the repeats in a clever way. Right, so for instance, you might have that phi of x equals phi of y. So for instance, and the point is, one of x or y. Okay. But they're able to give a sort of algorithm to do this in a useful way. So you can think of it almost as like modded out by some sort of equivalence relation or something. So eventually, I'm going to skip some details because it's just a talk and not a. Right, so you just have one representative from each element of the n-fold sumset. So remember, the n-fold sumset lives over here, but we're working in this space. So you have to think about what the set here looks like. So here you might have NA, and here you might have some set U sub n here. And you have to think about what this set looks like. Let's call this set. Okay, so I'm skipping the details about exactly how one does this, but anyways, if one's interested, one could look at their paper. I mean, it's an interesting to figure out what's going on. But anyways, so going forward, whoops, just all right. So you have this set, which is kind of cut in your n-fold sumsets. It turns out that this set is this. It turns out, I mean, the way they, not it turns out, but they defined it in such a way. Point is, U is an ideal. Now, you might know of ideals from a different area of math, but let me mention what an ideal is. Because an ideal is usually I mean, we know it from ring theory, but this is not the same thing. So it translation preserves the partial order. Okay, so we did all this work. The point is, all right, so let's go back to what we started with. We started with our set here. We turned it into a n-dimensional problem, and then by carefully choosing which element we cared about. So it could be the case that 20 elements in the domain map to the same element in the range, but we only pick one. But we choose it in such a way so that this set on the left-hand side has some structure. In particular, it's an ideal. This is what's going on. So once you have an ideal, there's a nice lemma. I think it goes by more than one name, but this is definitely one it goes by. Whoops. It's a structure theorem for ideals. So I guess this is pretty classical. The first place I've seen this is, I guess, in Cox, Little, and O'Shea's book on algebraic geometry. But it exists, yeah, it exists other places as well. I don't know why I wrote it. I think this is I think I just wrote something completely unrelated under translation. Yeah, it looked wrong. I had it. I had something felt wrong, but it's closed under translation. Yeah, translation. Okay. So there's a picture here. So, for instance, you might have so let's just say, perhaps people have seen this before, but let's get a picture. You might have your integer points. It has to be closed under translation. So it looks something like this, perhaps. And this will be your set W here. So you might take this to be W1, 2. Right, so U would be this whole set, everything over to the right. At least all the integer points. So Dixon's lemma is a way in d dimensions of picking out these points, the corners here. So the whole point and why the Nathanson-Ruja argument, so okay, not a problem. I mean that they're already there. This is basically the main idea. Their argument, or at least everything put together. But problem, at least if you're interested in effective bounds, so and it's my feeling that I mean it can't really be effective in general. I mean, it's just the nature of what it's saying. But it turns out one can kind of make it effective in our situation. So W is I shouldn't say is, but can be defined right. So this W can be defined by linear relations. Okay, maybe it's not so clear why this is true, but I mean, it just comes from the fact that phi itself is basically a linear map. Yeah. So you have to, I mean, okay, it shouldn't be obvious at all why this is true, but it turns out to be what's going on. So say basically, because should be a bit careful, but okay. Okay, so if you have a set defined by linear equalities and you want to have some sort of bound for these, I mean, oops. You might already know this off the top of your head, but you can apply Siegel's lemma. Okay, definitely oversimplifying here, but this is what's going on indeed. Okay, maybe not everyone's familiar with Siegel's lemma, so I should recall it. Apparently from memory, because I'm so confident that I could just remember. So this is Siegel. This is definitely a nice theorem. I mean, it definitely comes up. Enough. This is just one version of it. Okay. I'm not gonna worry too much of it. It's not super important what the bounds are. Now we'll say that as well, with some explicit bounds. So the point is you can find you can find an integer solution. You can find a so-called small integer solution. Yeah. I guess this version you can just prove by pigeonhole. So yeah. Anyway, so good. So it turns out applying some version of Siegel's lemma. I mean, okay, we can't just apply this as a black box. There's definitely some issues here, but you can finesse it into a way that it's applicable to our problem. You're able to eventually bound these W's here, which remember look something like this. And it turns out that just having a bound for these W's is enough to, eventually this turns out to be enough. So okay. Good. I think, yeah, so I think I don't mind stopping a bit early and then giving some more time for questions if people have them. So I'm happy to stop here.